Hi class, today I wanted to talk to you about refraction in your Refraction Lab, the lab number 11 that you have to do a report on. This is due soon. And so refraction is the bending and or change in speed of a wave when passing into another medium. So if you take a flashlight or like a laser beam and shine it into a swimming pool in the water, you're going to see how it bends. And so that's what we're studying. We're studying how it bends, but also we can see how it changes speed. So here we have a red laser shined at the interface between air and water. The water's kind of calm, so it's flat there. And we draw this normal line. This normal line is an imaginary perpendicular line perpendicular to the surface here. We measure angles off the normal line. So this right here, this would be called the incident angle. And when the light goes into the water, it actually changes direction. That's called refraction. And this angle is called the angle of refraction. Angle of incidence, angle of refraction right there. And there's a pattern. Whenever light passes from a medium that's, if you will, less dense or a lower index of refraction to something greater, it will always bend towards the normal. And if it were to go the opposite way, it would bend away from the normal. Here in this picture, we have air and we have water. Air has an index of refraction of about 1, and the reason is this relationship right here. N is a ratio between the speed of light in vacuum to the speed of light in the medium. So in air, we get a value of 1 because air doesn't really slow down, or we say light doesn't really slow down when it goes into air. So the speed of light in vacuum and the speed of light in air are basically about the same. So N is 1 for air. But in water, it slows down dramatically. And so if you put 1.33 here, if you put the speed of light here, which is referenced right there, you could solve for the speed of light in water, which is considerably slower than in vacuum. Now here's another illustration. This would be like a problem. We've got a ray of light coming in here, and it's drawn as a ray. We have theta 1, our incident. We have over here the ray coming out, the refracted ray. We have theta 2 here. And that normal line, always make it perpendicular. And if you have a protractor, you can draw a perpendicular line, and you can use that protractor to measure theta 1 and theta 2, which you'll kind of be doing in our lab. Here's another illustration. If you have a ray of light that's actually in a medium that's more dense, so here's just an example of a ray of light in glass, clear glass, going into water, 2 different mediums. But notice the glass has a larger index of refraction than the water. So look at this red ray. When the light comes up, hits the boundary, it bends away. It's going to something less dense. If we increase the angle, and look at this green ray now, when that light hits the boundary, it bends away. But it bends a little bit more than the red ray did. And we look at the blue ray, when it hits the boundary, it's bent away, but it's reached a limit here. When it bends right across there, and that becomes 90 degrees, we call this angle the critical angle. So the critical angle is the angle at which when light hits the boundary, it no longer escapes. And at that point, we talk about total internal reflection. Look at the black ray. That light ray is at a greater angle than the critical, so when that light ray hits the boundary, that light never gets out. It just bounces right back in. So it's reflecting, not refracting. So the red, the green, and the blue rays, they all get out, the different degrees here, but they all refract. But beyond that critical angle, light just bounces back in. Here's just a visual of this. Kind of the same diagram we had before, but here is the picture of a turtle, and you can see that light above right there. That is an image of the turtle, a virtual image of the turtle, but that's because the light is beyond the critical angle. So the way this works is light is coming from the turtle, and let's see the turtle's fin right there. Light's coming from the turtle hitting the water, but then it's bouncing back down into the camera's eye, whoever took the picture here. And so we see the ray of light as if it came from above here. So that's an example of beyond the critical angle, that total internal reflection. So here's your lab setup. We have this dish here, this semicircular refraction cell. And so this is one way you could do your lab. you could take a laser pointer and you could have that ray of light coming straight along, hitting that circle at the center here, and as it passes from air in the water, or whatever that might be, the cooking oil, it will bend towards the normal, and it'll come straight out here. So if you are able to trace this, draw a line right there to represent the boundary, draw maybe a dotted line to represent that normal line, and you can use a protractor to measure this. And to mark a ray like this, it's light, and light doesn't stay still. So if you have the light beam right there, take a little pencil and put a little dot there, put a little dot there, and then put a little dot over here, so that when you move the laser, you can use a straight edge to trace this ray, and then where it hits the boundary, you can use this dot to trace that ray. And once you have these two rays traced, come back with your protractor and measure the incident and the refracted angle. So this is one way you might want to set up your lab. On this screen here, you can look at the critical angle. If you reverse the ray, so let's say your laser pointer shines up, and now it's water into the air. At this point right there, when it's in the water, if it's beyond the critical angle, or you can actually get to the critical angle where that ray of light bends so much to 90 degrees. So that's a good way of measuring the critical angle. One thing to note here is that when the ray of light goes from the air into the cell right there, the reason why it doesn't bend at this point is because it's hitting perpendicular. And so if it's perpendicular to the surface right there, it'll just pass straight into the water. So we don't see refraction taking place right there, or at least no bending of light. So hopefully that helps you with your lab setup. There's some good pictures in the lab we look at. Like, for instance, this is a picture of the lab right here, and you've got this video you can watch. This is pretty important. And you see how they've got the cell there, and they've got a normal line drawn, and they've got the boundary drawn. And when they shine that ray of light here, this right here, that would be your theta 1, the incident. And over here on the outside, that would be your theta 2. Notice it became less. You're going water into air. So this would be one way of doing it. And by measuring a couple of these angles, maybe 6, maybe 10 angles, theta 1, theta 2, making a table of that, you could then make a graph and make a graph. Let's look on the next screen here. So if we're going to determine the index of refraction for water and for cooking oil, we really want to make a table of values where over here you're going to look at theta 1, and over here you're going to look at theta 2. And just flat out, just measure those angles. Now once you've got that off to the side, then maybe make another table. And let's say we're looking at the water. Make another table. And so this time, find the sine. And if you have a calculator, just use the sine right there. We'll say the sine of theta 1. Okay, put that right there. Sine of theta 1 on this side. And then over here, put the sine of theta 2. Okay, so for whatever you're doing, if you're doing water in the air or water in the cooking oil, make a table of the thetas, theta 1, theta 2. Then make another table of the sine of each one using your calculator, and then make a graph. So if you graph the sine of theta 1 versus sine of theta 2 on the axes like this, you'll likely see a linear relationship, hopefully. Something that looks like this, with some degree of slope, someplace, okay? And that slope has significance. From that, you can actually figure out what the index of refraction is of the water or the oil. So this right here, this is called Snell's law. Snell's law is well established, and you've got it in your lesson notes right there. Well, Snell's law is this. N1 sine theta 1 equals N2 sine theta 2. And in your lab, when you do your graph would be of the form y equals mx plus b. And so if you kind of rearrange this, because this sine of theta 1 on your graph should be on the y-axis. And then you have your equals. And then what's your slope going to be? Well, your slope would be some numerical value in there, but it has significance. What's the x? Well, the x-axis has this on it, right there. And if you look at your graph carefully, the intercept should probably be 0. So we have this relationship here. And if you look back at Snell's law right there, if you divide n1 over into the other side, then this right here, this would be the ratio of n2 over n1. Now what's n1? Well, this right here, that n1. That n1 right there, that value, that should be air, right? And what's the index of refraction of air? Index of refraction of air is 1. So whatever you get for your slope is basically the index of refraction of your water or your oil. So hopefully that helped, guys. Thank you.